Okay, so in the second part of this chapter, we're going to deal a lot with titrations. So we've talked about titrations before. The way that we have utilized titrations in the past and things like 151 is we have had, let's say, some sort of unknown concentration. So let's say that we had a base, something like sodium hydroxide, and we didn't know what its molarity was, what its concentration was, but we had an acid, let's say this was something like HCl, and we did know its concentration. So this was our known value. So in acid-base titrations before, we would be able to utilize our known concentration to determine the unknown concentration of whatever we were looking for, right? And so what that really heavily relied on was our use of what is called a pH indicator, right? So at a pH indicator, what that thing would do is it would turn our solution a color when we reached the equivalence point. So at the equivalence point, the number of moles of acid were equal to the number of moles of base. We are able to utilize all of that information, again, to go back and determine the concentration of the unknown. Okay, so that, again, is how we have utilized acid-base titrations in the past. We've used an indicator, and it's only been to look at concentrations of things and not necessarily the pH of things. So now, in this chapter, we're going to take titrations a little bit further, and we're going to be essentially monitoring the pH throughout the entire course of a titration. And what we're going to be able to generate from that is something called a pH curve or a titration curve. So another word for these pH curves is titration curves. Okay, so what do those actually look like? Okay, so we're going to spend some time with these with respect to these pH curves or these titration curves. And most importantly, we're going to go over two different types of titrations. We're going to talk about first, which is what I'm going to talk about today, the titration curve that is going to be generated when you titrate a strong acid with a strong base. And then in class, we're going to go over kind of the more important type of titration curve, which is the titration curve for a weak acid being titrated with a strong base. Okay, so again, what do these guys look like? So we're going to start with a strong acid and a strong base. And so to highlight what titration curves will look like, over to the right here, I have the titration curve for a strong acid, strong base titration. So the strong acid was HCl, and the strong base that we used was sodium hydroxide, okay? Okay, so experimentally, what type of setup would we have that would actually generate stuff like this? So if you want to imagine what's happening in these overall titrations, for this type of titration, you would have your strong acid, so this is going to be HCl, in, let's say, an Erlenmeyer flask or some sort of beaker or something. You would have your burette, as usual, and the sodium hydroxide, the strong base, would be coming from your burette, and you'd be measuring volumes of sodium hydroxide released. Instead of having an indicator, right, instead we're going to have a pH electrode and a pH meter, right? And so we're going to be measuring essentially the pH as we add volumes of sodium hydroxide from the burette, right? So our plot here is pH as a function of the volume of sodium hydroxide added, or just the amount of sodium hydroxide added, okay? So there's going to be a couple of different points in this curve that are going to be important. So number one is the first point right here. So this is something that we'll call the initial pH, okay? So initial pH, or initial point in this titration curve, is essentially just going to be the pH of the HCl before we've actually added any type of NaOH, okay? Another important point is the equivalence point. And so for these titration curves, the equivalence point manifests itself as this sharp inflection in this sigmoidal curve, right? So we start at very low pHs because we have a very acidic solution. The pH is going to just kind of slightly increase as we continuously add NaOH until we reach the equivalence point, and we'll see this sharp rise in pH at the equivalence point. And then after the equivalence point, we get the second or third region, which we will just kind of categorize as after the equivalence point. Okay, and so we're going to calculate the pHs of this solution, of this titration, at these various different points along this curve. Okay, so where do we usually start with respect to these titrations? So what I always tell everyone is always start by calculating the equivalence point in the titration. Okay, so as a reminder, what the equivalence point was and what we've known as the equivalence point up into this point in time, the equivalence point was the period in time or the point in time in a titration where the number of moles of acid equal the number of moles of base. Okay, so that's not going to change. It's still going to be the exact same definition. Number of moles of acid equal number of moles of base, except what we're going to be calculating now for this equivalence point is not necessarily moles or concentration or anything like that. Instead, we're going to be determining the volume of base required to get to this point. Okay, so for these titrations, the equivalence point kind of takes on a new definition, and we're going to look at it as the volume of base required to reach the equivalence point. Okay, and so for all of these titration curves, I always suggest that you start at this point in time by taking whatever information you have and calculating the volume of base required to reach the equivalence point, which is what we essentially determine to be the equivalence point, okay? So let's say that we have a titration. So we've got HCl. We've got HCl in our little flask, and we know, it's a really ugly flask, we know the volume of this HCl solution. So there's 25 milliliters of HCl in this flask, and it has a concentration of 0.1 molar. Okay, so again, this is our strong acid. To that, we are adding our strong base. So this is sodium hydroxide. We're going to be adding volumes of the sodium hydroxide from our burette. And this guy, our strong base, has a concentration of 0.1 molar as well. Okay, so now the first part, what we're going to do is calculate the volume required to reach the equivalence point. Okay, so again, we're going to utilize our definition, or our working definition of what an equivalence point is. Number of moles of acid equals number of moles of base. So to utilize that, we're going to take what we know, our volume and our molarity of the acid, and we're going to calculate how many moles of acid are actually in here to begin with. Okay, so again, molarity is defined as the moles of solute divided by volume in liters of solution. So we know the molarity of our HCl. This is 0.1 molar. That's going to be equal to the number of moles of HCl that are in there, divided by the total volume, and that total volume needs to be in liters, right? So for this HCl solution, we have 25 mils. Converted to liters, that is 0.025 liters, okay? So this is for our HCl, or the acid. So I'm going to solve for X. X ends up being 0.0025 moles, and that's going to be of our HCl. So that's how much HCl was initially in our little flask. Now we're going to utilize that information to determine how much NaOH we need to add to essentially give that exact same number of moles of NaOH, right? So again, at the equivalence point, 0.0025 moles of acid is going to equal the same number of moles of NaOH, of our base. So it's going to be equal to 0.025 moles of NaOH. So now we know how many moles we need to supply of our sodium hydroxide from the burette. To calculate the volume, we're also going to take this. We're going to take our number of moles as well as the molarity of the sodium hydroxide to calculate what volume is required to reach that point in time. Okay, so for sodium hydroxide, we know that our concentration is 0.1 molar. Again, the question that we're asking is what volume are we going to need to give us this same number of moles, this 0.0025 moles of NaOH. 0.0025 moles of NaOH. And so we solve for x. X ends up being 0.025 liters, which converted to milliliters is 25 milliliters. Okay, so again, we've got 25 mils of our HCl in the flask. And we're saying how much of this NaOH is going to get us to the equivalence point. That's essentially what we have just solved for. Okay, so 25 mils of NaOH is what is required to reach the equivalence point in this titration. Okay, so that's usually step one. Now, step number two, after you've calculated that equivalence point for the titration, you're now going to go in and start to calculate the pH at various volumes of sodium hydroxide added. Okay, so the first one that you're usually going to calculate is just going to be the initial pH. And so the initial pH is the pH whereupon we have only added 0 NaOH, right? So it's just the initial pH of the HCl solution. So again, for our little HCl solution, we know HCl is a strong acid. So it completely ionizes to form H3O plus Cl minus. In this initial solution, right, just HCl, we haven't added any sodium hydroxide from the burette. It had a concentration of 0.1 molar. If I want to calculate the pH of the solution, I need to know the hydronium ion concentration, right, the number of protons, the number of H3O plus. Since this is a strong acid, I can assume that all of it goes to form products. So my concentration of H3O plus is also 0.1. My concentration of Cl minus is also 0.1, but that doesn't necessarily matter, right? So now to calculate the pH of this, all I need to do is take the minus log of my concentration of H3O plus, which is the same exact thing as just the concentration of initial acid. And that gives me a pH here equal to 1. Okay, so first point in this titration, calculating the initial pH before we've added any NaOH is just going to essentially be calculating the pH of this acid solution, right? You just take the minus log of the concentration of strong acid, and that is your first pH. Okay, so now after we have calculated the initial pH, we're going to move on and we're going to start calculating the pH after we start to add sodium hydroxide from the burette, okay? All right, so again, to kind of illustrate the situation, we've got our flask. It has a certain number of moles, right? So we know that the HCl had a volume of 25 milliliters. It had a concentration of 0.1 molar, okay? And then we've also already calculated the number of moles. So we did that when we calculated the equivalence point. This ended up being 0.0025 moles of our H3O plus, our HCl, okay? All right, so again, this is that initially. Now what we're going to start doing is we're going to start adding NaOH from the burette, okay? So let's say that we start by adding only 5 milliliters. So we add 5 mils of our 0.100 molar sodium hydroxide. So now to calculate the pH of this resulting solution, so we're going to add 5 mils to our flask, and again we're going to measure or calculate the pH. We need to consider what type of reaction is actually going to be taking place between the sodium hydroxide and the HCl, right? So in this reaction, for every 1 hydroxide molecule or mole that we add, we're going to react with an H3O plus to form water. Okay, so this is kind of like what we're doing right now is looking at the overall stoichiometry with respect to what we had and what is left over after we've added this amount of sodium hydroxide. So we're kind of questioning right now what we had, what we've added, and then what's left over to get the new pH for the solution. So to move into this type of stoichiometry-based problem, we first need to calculate how many moles of sodium hydroxide have we added when we have added 5 milliliters of this 0.1 molar solution. Okay, so to do that, we'll go back to the molarity. So molarity of this sodium hydroxide solution was 0.1 molar. We're going to calculate the number of moles of hydroxide, that we have added when we have added 5 mils. And again, when we take our 5 milliliters, we're going to convert it to liters. So that is 0.005 liters. All right, so now if we take the concentration, we multiply it by the volume, we're going to get the number of moles of sodium hydroxide added. That ends up being 0.0005 moles of OH minus. Okay, so we had this much, H3O plus. We've now added this much of OH minus. So what we're going to do is we're going to make this little table, and we're going to call this a BCA table, before, change, after, to kind of keep track of what we had, what we have left, and then calculate the pH from that. Okay, so we're going to take our little reaction up here, our little stoichiometric reaction, where we have our OH minus reacting with our H3O plus, going to form water. And we're going to write over to the side BCA. So please do not confuse this with an ice table. All this is like kind of like a record-keeping type table, right? We're going to say what we had, what we've added, how it's changed, and what we have after. So B here stands for before, C stands for change, and then A stands for after. And again, this is not an ice-based thing, so we're not going to be using any type of X's or anything like that. All right, so before, with respect to H3O plus, that is the initial amount of moles of H3O plus that we had. So we've already calculated that. So that was 0.0025 moles of H3O plus. And what we're also going to write in for before is the amount of OH minus that we have added. So we have now added, when we added the 5 milliliters, 0.0005 moles of OH minus, okay? So now, we're going to look at this, right? We're going to say, okay, we had this much, we have added this much. Which one is the limiting reagent, right? When these guys react, which they're going to, one of them we are going to run out of first, okay? And so that one, or that limiting reagent for this problem, is the OH minus. There is much less of it comparatively to the H3O plus. And so the limiting reagent is going to define the change here, right? So for every one of these, we're going to utilize one of these, and we're going to make 2 of these. For this type of problem, we don't care about water because it's not going to do anything, right? We're just essentially keeping track of H3O plus, OH minus using this table. All right, so because of that, our OH minus, because there's less of it, we're going to use it all up entirely in the reaction. So we're going to lose that much of that guy. We're also going to lose the equivalent amount of our H3O plus. So after this reaction has occurred, we have 0 of the OH minus, but now we have 0.0020 moles of our H3O plus. Okay, so again, how many moles do we initially have of H3O plus? How many moles of OH minus have we added? And then what's left over when they fully react? All right, so we are left with H3O plus. So now if we want to calculate the pH of this new resultant solution, we're going to take the moles that we have left over after this reaction, and we are going to calculate the pH utilizing that, right? So there were 0.0020 moles of H3O plus left over. To calculate the pH, we need the concentration of H3O plus, right? Right now, all we have is the number of moles. So now to calculate the concentration, we need to take one little piece of information back into play here, and that's going to be the volume, right? So molarity, again, is moles per liter. So to get our new concentration of H3O plus, we're going to take the number of moles that are left, and we're going to divide it by the volume of the solution. So now it's important to note this is the volume of the new solution. So new solution. So that's going to be the addition of the volume that we originally had, right? So there was originally 0.25 or 0.025 liters, but now how much have we added? We just added 5 milliliters of volume, right? So we're going to have to add that in when we calculate this new volume and then when we calculate the concentration overall. So this guy on bottom is going to be the initial volume plus whatever we have added, which for this problem was 5 milliliters or 0.005 liters. So when we do that, we're going to get a new H3O plus concentration of 0.0667 molar. Once we have our concentration of that, to calculate the pH, all we need to do is take the minus log of that. So minus log of 0.0667 gives us a pH equal to 1.18. Okay, so lots of little bits and pieces at play here. We had initially HCl. We have now added a volume of sodium hydroxide to our flask, right? We had to calculate, using the stoichiometry of the reaction, how many moles of H3O plus we had left. So that's what I did on the last page. And then to get the new pH, we're going to take those moles, and now we had to redivide it by our new total volume to get the new concentration, and then take the minus logarithm of that to get the pH. All right, so we can continue to do that as we move further and further into this titration, right? So we just calculated the pH after adding 5 mils of sodium hydroxide. We could do the same thing after adding 10, 15, or 20 mils of sodium hydroxide. We can use the exact same method by which we utilize for 5 mils, right? So let's say that we've moved on in this titration, and now we have added 15 mils of sodium hydroxide. How do I calculate what the pH is after this 15 mil addition? So we follow the exact same format. The first step in this would be determining the number of moles of NaOH added when we have added this 15 milliliters. So to calculate that, we would take the concentration of our sodium hydroxide solution, and we would multiply it by the volume that we have now added to solve for the number of moles. So 15 milliliters converted to liters is 0.015 liters. When we solve for X, which again is the number of moles of hydroxide ion that we have added, this ends up being 0.0015 moles of OH minus. So we would then take that and we would go back to our little reaction, our reaction stoichiometry. So OH minus plus H3O plus goes to make water. We would write the beforehand number of moles, right? So again, for H3O plus, that came from the original calculation. Originally, there were 0.0025 moles of H3O plus in our little flask. We have now added 0.0015 moles of sodium hydroxide when we have added 15 mils. And so again, the change is going to be determined by who is the limiting reagent, right? Who are we going to run out of in this reaction? For this one, it again is the sodium hydroxide. This 0.0015 is less than the 0.0025. So we're going to completely run out of that one. So that's going to give us a number of moles of hydroxide ion as 0 afterwards. And we're going to subtract the exact same number of H3O pluses away from the before amount, right? So that's going to leave us with 0.001 mole of H3O plus. And again, we don't care about water at this point in time. So that's how many H3O pluses we have left. To calculate the pH, we then need to take that and calculate the concentration of H3O plus in our new solution, right? So we know how many moles we have. Now we just need to divide that by the total volume of the solution. So again, this was the 25 milliliters that was present originally, plus the addition that we have made. So this is now 15 mils. So 25 plus 15. So 25 plus 15 mils gives us 40 milliliters. And when this is converted to liters, this is 0.040 liters. So our number of moles of H3O plus divided by the volume, the new volume, gives us a concentration equal to 0.025 molar. And so then for the pH of this, we just need to take the minus logarithm of our concentration, which gives us a pH equal to 1.60. So again, multiple steps involved here. Number one, we need to calculate the moles of strong base that we have added, given whatever volume and whatever concentration we have added. We need to then utilize that to calculate the number of moles of H3O plus left. With that, we're going to calculate the new concentration of H3O plus by including the total volume. And then once we know that, we're just going to take the minus logarithm of it to give us the pH overall. Okay, so we can continuously do that, right? So we calculated the pH of this titration at 5 mils. We calculated it at 15 mils, right? But for any point in time between the initial pH, which is what we calculated, and the equivalence point, which is something that we've also already calculated. So just as a reminder, for this titration, the equivalence point was going to be at 25 milliliters. So at any addition between the initial pH and the equivalence point, we're going to calculate the pH in the exact same manner. We're going to figure out how much OH minus we have added, how much H3O plus is left over, and then what is the new concentration of the H3O plus, and then the pH from that. Okay, so for example, I give you the pHs for 10, 15, 20 here, but I could also ask you about the pH of this titration at 17.5 milliliters of NaOH added. Okay, so again, you go about answering that question in the exact same format that we did for 5, 15, so on. All right, so then after that, we hit the equivalence point, right? And so at the equivalence point, which is 25 milliliters, which is something that we've already calculated. So at this point, the number of moles of OH minus that we have added are now numerically equivalent to the number of moles of H3O plus that were there to begin with, okay? So we go back to our little equation. We had OH minus plus H3O plus, right? They go to make our little water. They neutralize each other. And so at this point in time, at the equivalence point, the number of moles that we have for OH minus is equal to the number of moles that we had for H3O plus. So they have completely canceled each other out, right? Both of them are gone entirely. They have both neutralized each other. And so the only thing that we have left in solution at this point in time that is going to affect the pH of the solution is just water, all right? So all is just going to be, again, just water, right? And so we know what the pH of water is, right? Because for water, we have equal concentrations of H3O plus, OH minus. Both of those have concentrations that are equal to 1 times 10 to the minus 7th. So the pH of water and the pH at the equivalence point in this titration is just 7. It's just neutral, all right? So for any type of strong acid, strong base titration, the pH at the equivalence point is always equal to 7. Again, because at the equivalence point, the only thing that's left in solution is water, and water has a pH of 7 due to its autoionization. So we can go ahead and plot that on our titration curve now at pH equal to 7 at our equivalence point, right? So now we've started to form this sigmoidal shape to our curve. All right, so now we've reached the equivalence point. That's great. What happens as we move past the equivalence point? So let's say that we move past the equivalence point. The equivalence point was 25 milliliters, but now we're going to continue on in this titration, and we're going to move on to a volume of sodium hydroxide added of 30 milliliters. How are we now going to calculate the pH of this solution? Right, so it's going to be the exact same initial starting point that we've done for all of these other volumes, right? I'm going to take my volume of sodium hydroxide. So I've got sodium hydroxide. I've added 30 mils at this point in time. I'm going to take my volume and I'm going to multiply it by the concentration to solve for the number of moles of OH minus that I've added. All right, so 30 milliliters converted to liters is 0.030 liters. And so after adding 30 mils of sodium hydroxide, I have added 0.003 moles of OH minus. Okay, so same exact thing that we have just done. You figure out the number of moles of strong base that you've added to this titration. Now we're going to go back to our little stoichiometry table. We're going to write our reaction. H3O plus goes to make 2 waters. And we're going to go ahead and fill in our before, right? So when we add these two things together, we have added 0.003 moles of OH minus, and we initially had 0.0025 moles of H3O plus that were in the flask at the beginning of the titration, right? And so now, after we've moved past the equivalence point, something has changed. Now, the H3O plus is our limiting reagent, and the OH minus is our reagent in excess, okay? So because of that, the change is not going to be defined now by the OH minus, but instead by the H3O plus. We're going to completely run out of H3O plus, and we're going to have an excess amount of OH minus left in the flask afterwards, right? So when we calculate this, we find that we have 0.005 moles of OH minus, nothing here in this guy, okay? So now the OH minus, the excess amount left in the flask after we have passed the equivalence point, is what is going to be determining the pH of our solution moving forward. So now what are we going to do with this excess OH minus? So we're going to take those number of moles that we had. So we had OH minus. After our H0 plus and OH minus had completely reacted, we were left with 0.0005 moles of OH minus. And we're again going to calculate now the concentration of OH minus, right? We'd been calculating the concentration of H3O plus before. Now that's going to change, and we're going to calculate the concentration of OH minus. So this is going to be the number of moles of OH minus divided by the total volume of the solution. And so total volume here is going to be again, the volume that we initially had in our flask before we started the titration. And now we're going to add to it the volume that we have added from the burette. All right, so total volume is 55 milliliters, which is equal to 0.055 liters. So we're going to take that and we're going to divide our number of moles by that total volume. And that's going to give us a concentration. Of course, I didn't do this. So 0.0005 divided by 0.055 gives us a concentration of 0.0091 molar. Okay, and this is OH minus concentration. All right, so now we still want the pH. We're still measuring the pH of the solution. We have the concentration of OH minus, and we know some relationships between OH minus and H3O plus and then therefore pH as well, right? So right now, what I'm going to determine is the pOH, right? I'm just going to take the minus logarithm of my OH minus concentration. That's going to give me a value equal to 2.04. And then I also know that pH is equal to 14 minus pOH. So I'm going to utilize that relationship to calculate pH. So 14 minus 2.04 gives me a pH here equal to 11.96. So then we can go to our little 30 mils of sodium hydroxide and plot our 11.96 pH. Looks like it's like above that. Anyway, okay, so that is how you would go about calculating the pH after we have passed the equivalence point. So now we have OH minus as the excess reagent. It's going to be dominating the pH of the solution. And so to calculate the pH, you have to take in its concentration or calculate its concentration, calculate the pOH, and then get the pH from that. And so you can continue to do that for however many milliliters past the equivalence point you want to go, right? To get this nice, beautiful little S-shaped sigmoidal curve. Okay, so that is the overall titration, right? We started initial pH before we had added any sodium hydroxide. We calculated the pH in between the initial and the equivalence point, and then I also showed you how to calculate the pH after you had passed the equivalence point. And so overall, for these types of strong base, strong acid titrations, right? So we have our acid in the flask initially. We are titrating it with the strong base. There are, again, going to be certain little regions that you guys should be familiar with calculating the pH for. The first region was the initial pH before we added any sodium hydroxide. The second region is in between the initial pH and the equivalence point. So this is when we have H3O plus in excess. The third region is the equivalence point, and you shouldn't have to do anything for that besides know its value, know what volume you need to add of sodium hydroxide to get there, but the pH of the equivalence point is always 0 for this strong acid, strong base titration. And then after the equivalence point, that is the fourth region, we have OH minus in excess. So again, I demonstrated how you would calculate the pH for that region of the curve. Okay, so this is a nice little summary slide that kind of just writes out in words what I just stated on the previous slide. So feel free to look at this on your own. And then in this last little bit, we have another titration, all right, practice. And so I would suggest that you maybe go over these problems. They will probably likely be on the quiz, all right? So in this titration, in this practice titration, I give you a solution of hydrobromic acid. It has a concentration and a volume, and you're going to be titrating it with a solution of potassium hydroxide. So again, if we draw out what this would experimentally look like, the HBr is going to be in our flask. It has a concentration of 0.175 molar and a volume of 35 milliliters. So this is our initial solution. We are going to be titrating it with potassium hydroxide, given volumes of potassium hydroxide that has a concentration of 0.2 molar. Okay, so for the quiz, I will go ahead and tell you exactly what you will need to know. I will probably have you calculate the initial pH of this titration. I will probably have you calculate the volume of the potassium hydroxide that's required to reach the equivalence point. I will have you calculate this guy. And just as a give me, because I've said this already, you should be able to know this immediately, I'll probably have you tell me what the pH of the equivalence point would be for this titration, given that it is a strong acid with a strong base. Okay? All right, so in this last little slide, we have been titrating a strong acid with a strong base, right? So the acid has been in our flask the base has been in our burette, and we've been adding base to acid in this overall titration that we've been talking about. We can also do the reverse, right? We could have a strong base, and we could titrate it with a strong acid. So what do I mean by that? So let's imagine that in the reverse, we've got our flask, and it has our base. So let's say this is something like sodium hydroxide, and to it, we are adding a strong acid. Let's say this is something like HCl. Okay, we can also calculate the pH at various stages along this titration curve, right? It's only going to be different with a couple different respects to what we were doing before, right? So, for example, if we had this strong base, strong acid titration, and we initially measured the pH, then the initial pH would be very basic, right? Because we would have not added any HCl at first. And so in the titration for this, we would start initially at a very basic solution, right? Again, the equivalence point, regardless, would still be 7 because it's strong base, strong acid. At the equivalence point, there's only water left around to influence the pH of the solution. The pH of water is 7. And so still, the equivalence point would have a pH equals 7. But in going between the initial pH and the equivalence point for this strong base, strong acid titration, the initial parts here have OH minus in excess, right? So you would have to go about calculating how much OH minus is in excess at each given volume along this part of the curve. You'd have to calculate the pOH from that, and then you would get the pH from that. Equivalence point again is the same, but then once we move past the equivalence point, in these type of titrations, we have H3O plus in excess, right? So it's, again, with this strong base, strong acid titration, the titration curve is similar. It's just kind of like the inverse of what we saw before. So we start basic, we go towards more acidic, and then once we move past the equivalence point, we are now in this acidic region. I usually don't ask a strong base, strong acid type question, right? So this is just letting you know, hey, this is what the curve would look like. I'm probably not going to ask any type of questions related to this. And then finally, if you guys wanted more practice, there is a question. This is going to be a strong base, strong acid titration, right, where we have the strong base. We're going to start very basic. Initially, we're going to be adding acid, strong acid to that strong base. So again, we would get a nice titration curve like this, the inverse of what we saw for the strong acid, strong base. If you want to go ahead and practice with some of these problems, feel free, but I am not going to go over those in this presentation. And so I think that is it for now. So again, this entire video was going over the titration curve and how you could calculate the pH at various regions along the titration curve of a strong acid being titrated with a strong base. I have given you indication of what questions I'm going to ask on the quiz, so make sure to go back and be capable of calculating those before you start the quiz.